As mentioned, the topic of the presentation is the comparative study of Suzhou Zhongnan Center and earthquake outbreak.
本次汇报主要包括以下几个内容：第一部分是引言，第二部分是抗震设计参数，第三部分是抗风设计参数，第四部分是抗震及抗风设计对比，最后一部分是结论。
And this is the agenda of my presentation.
先介绍一下本项目。中南中心它是位于苏州金鸡湖 CBD 核心区的。
And first of all, to introduce this project, the Zhongnan Center Tower is located in the CBD area of Suzhou Jinjilan.
它一共有137层，建筑高度729米，结构高度598米。
And it is a building of 729 meters high with 138 stories with 597 structural height.
它是框架核心筒结构体系。
And the structure is frame core wall structure.
核心筒的平面尺寸为34.1米乘以34.1米。
And the area of the core is 34.1 times 34.1 meters.
这幅图是那个中南中心项目加强层的那个典型的图。
This is the plan of the reinforced structure.
它包括有8根巨柱、4根角柱，还有中间的回字形核心筒。
And it has 8 mega columns and 4 corner columns with a core in the middle.
另外还有升地行架和环架行架。
Also have belt truss and outriggers.
由于超高的高度以及超长的自震周期，中南中心对于长周期的地震动是非常敏感的。
Well, because of the super top height and a long structural period, the Zhongnan Tower is very sensitive to long period ground motion.
目前国家的抗震规范中和反应谱中对周期超过6秒的情况没有给出地震作用的取值。
The seismic action parameters of response spectra for period ranges longer than 6 seconds are not even provided in the Chinese code for the seismic design of buildings.
对于非常重要的建筑，就像中南中心大厦这种，在进行抗震设计时，需要综合安全报告和规范的规定来确定合理的地震作用参数。
For crucial building projects such as the Zhongnan Tower, it's required that both the site-specific spectrum and the code-specified design spectrum be investigated for the seismic design.
因为地震作用和负荷载的取值，地质结构周期是非常密切相关的。
Because the seismic action and the wind loading spectra are closely correlated.
这张图是表示结构周期为1秒到10秒的高层结构以及超高层建筑对地震的和风设计的反应谱的对比。
And this is a comparison between seismic action and wind loading spectra for tall buildings and super tall buildings within the time period of 1 to 10 seconds.
从这张图上可以看出，风的主导频率是比较低的，而且是主要位于高层以及超高层的频率范围之内。
As you can see, the frequency of wind is relatively low and mostly influencing tall and super tall buildings.
通常超高层结构会考虑高阶阵型的贡献，而对于高层建筑，只有低阶阵型会受到风的激励。
And for super tall buildings, it's basically the lower structure will be influenced by wind.
相比之下，地震主要激励的能量发生在低层建筑的频率范围，或者是高层建筑的高阶阵型中，因此必须要考虑大量的阵型。
And on the other hand, the seismic action will influence super tall buildings on the lower part. Will influence the lower buildings and the top part of the super tall buildings.
以下是介绍一下中南中心项目的抗震设计参数。
Now I want to talk about the seismic design parameters for Zhongnan Center Tower.
在多域地震和涉港地震和海域地震，分别是以50年设计基准期来作为抗震设计的。
And in our design, the return period was regarded as 50 years for frequent earthquake, moderate and rare earthquakes.
它们的超越概率分别是63.2%、10%和2%到3%。
As shown here, the POE is 63.2%, 10%, 2 to 3%, respectively.
中国的型钢混凝土结构技术规程中，建议这种混合结构的总拟比是为4%。
And the damper ratio is suggested at 4%.
这个是没有考虑结构高度以及它的扩展作用这些。
And this ratio is not with the consideration of its structural height.
日本大量的实测结果表明，结构会随着它的高度的增加，它的总拟比会逐渐的减小。
And from the research in the case studies in Japan, it shows that with the increase of the height, the damping ratio will decrease.
中南中心项目的周期折显系数在小镇下取的是0.85，中镇取的是0.95，大镇取的是1.0。
And the period reduction factors for this project is 0.85, 0.95, and 1, respectively.
主要是考虑在中镇和大镇下隔墙有一部分的损坏，所以周期折显系数会有一定的增大。
And the factors that is actually increasing with the moderate earthquake and rare earthquake.
目前大部分的总拟比现场实测均在脉动荷载条件下获得的。对于比较高的荷载输入水平，就像50年一遇的风荷载、多余地震、涉防地震和海域地震，因为它结构响应水平比较高，结构内在耗能能力增加，会使它的总拟比有所增加。
The damping ratio tests are mainly obtained from site measurements and vibrations for actions and loads of high amplitude, such as the 50-year return period, wind load, frequent earthquake, moderate earthquake, and rare earthquakes. The damping ratio will increase with the increase of energy dissipating due to large structural responses.
接下来介绍一下中南中心的抗风设计参数。
Now, I'd like to talk about the wind load design parameters for Zhongnan Center.
首先是它的层间位角限值是1%。
And the storage drift is 1/500.
它的舒适度控制指标是0.25米每20方秒。
And the human comfort ratio is 0.25 meters per square seconds.
体型系数取的是1.4。
Shed factor is 1.4.
地面粗糙度取的是 C 的。
Site exposure is type C.
它强度设计的回归期是100年，总拟比是3%。
The return period is 100 years and damping ratio is 3%.
刚度设计的回归期是50年，总拟比也是3%。
Return period for stiffness design is 50 years and the ratio is also 3%.
在进行舒适度验算的时候，它的回归期是1年，总拟比是1%。
And the return period designed for human comfort design is 1 year and the damping ratio is 1%.
最后我们计算下来的结果就是下面的这张表。
And as shown here is the results of our calculation.
我们进行了风洞试验和中国规范的对结构的机理简历和倾覆端距进行了对比。
We have compared the overall base shear and overturning moment and the wind tunnel test and the Chinese codes.
按照中国规范的那个风荷载下，机理简历会略大于风洞试验的结果。
And the results of the Chinese codes is a little bit higher than the results of a wind tunnel test.
风洞实验的倾覆端距的结果会略大于中国规范的结果。
But the overturning moment results of a wind tunnel test is higher than that of the Chinese codes.
接下来我们进行了抗震以及抗风设计的对比。
Now we compared the design methodologies between seismic action and wind loading.
首先，说明一下，目前提高结构的抗震安全性主要有以下的2种方式。
First of all, there are 2 methods to improve the seismic safety.
分别是提高地震作用，以及 加强抗震措施。
through the improvement of seismic action and seismic measures.
提高地震作用主要是通过更长的回归期来提高。
And we can improve the seismic action through achieving a longer return period.
抗震措施主要是通过内力放大系数以及就是一些抗震的构造措施。
And the improvement of seismic measures is achieved through improvement of earthquake resisting measures and internal force amplification factors.
但是在做提高结构的抗风安全性的时候，我们仅仅通过提高风荷载水平这一点来提高结构的抗风安全性。
But there's only one way to improve the wind safety, which is increase the wind load.
原因是在于就是在做抗风设计的时候，往往是假定结构是弹性的。
Well, the reason is when we do the improvement of wind safety, we assume that the structure is elastic.
最后我们进行了在100年的风洞实验荷载下以及多域地震荷载下结构基底剪力以及倾覆力矩的对比。
And we compared overall bed shear and overturning moment through wind tunnel tests and frequent earthquake.
多域地震的荷载下基底剪力略大于风洞试验的结果。
And the overall base shear and the frequent earthquake is higher than wind tunnel tests.
100年一遇风洞试验的倾覆力矩大于多域地震荷载下的倾覆力矩。
And as shown, the overturning moment of wind tunnel tests is higher than frequent earthquakes.
但是相差不是特别多。
But the difference is not big.
最后在涉防地震下，我们也进行了上述对比。
And we also conducted comparison and moderate earthquakes.
涉防地震的基底剪力基本是100年一遇的风洞实验的基底剪力的2.6倍左右。
As we can see, the overall base shear and the moderate earthquake is almost 2.6 times more than that and the wind tunnel tests.
它的倾覆力矩大概是100年风洞实验的1.9倍。
And the overturning moment is 1.9 times more than that of our wind tunnel tests.
接下来讲一下结论。
Now just to conclude.
在长周期段，多域地震最大影响系数应该按安全报告进行区分，而设计版图的形状应该按规范来进行计算。
Well, in the long period range, the maximum value will be applied in design with the site-specific results. The shape of design response spectrum can be set as the code-based design spectrum.
而总一体的取值应该考虑荷载类型、结构响应水平以及结构高度来综合确定。
And the damping ratio applied for seismic analysis needs to take the type of load structural response and height of structure into consideration.
超工程建筑的顺风向以及回风向荷载效应是非常显著的。
And the long and crosswind load effects are significant for super tall buildings.
风荷载参数应该结合规范以及风洞实验的结果来进行。
And the design parameters for wind loading could be obtained through careful comparison between code calculation and wind tunnel tests.
提高结构抗震安全性的方式通常包括提高地震作用以及提高抗震措施，而提高结构抗风安全性的方法通常是通过提高风荷载水平来实现。
As mentioned earlier, the measures to improve the seismic safety include the increase of seismic action and seismic measures, while the measures to improve the structural safety and the wind is only the increase of wind loading.
对于超高层建筑，风荷载结构响应通常高于多域地震下的结构响应，但是对于重要的超高层建筑采用中正弹性设计的情况下，涉防烈度地震下的结构响应会高于风荷载作用下的结构响应。
Although the structural responses due to wind loading are commonly higher than that due to frequent earthquake, the structural responses due to seismic action may prevail if high seismic performance objectives were selected for important super tall buildings.